And hello, welcome to IGM451 Systems, Concepts, and Games and Media. I don't think I nailed that. Anyways, welcome to IGM451 Systems, Concepts for Games and Media. My name's Idan Beck, and I am your online Spring 2020 teacher, instructor, what have you. You may already be asking, where the hell am I? And this will come up many times throughout the semester, so I'm going to address it. I am currently in a hotel room in Hong Kong where I travel pretty often for my job. Um, I'm also a little bit sick, but I will be doing my best to provide these lectures with whatever necessary support. I'm currently on a MacBook Pro, but I don't expect any coding to be done in this particular lecture, although when we need that, I'll make sure that I have a PC and whatever else is necessary. But hopefully the audio sounds good because of um, my cool AirPods. Anyways, let's jump in. I know this lecture is a little bit late, and I apologize for that. But this first week of content for this class will be largely syllabus and introductory, and we'll start to get into more real stuff in the coming week. And so hopefully the delay is not going to be too impactful. So let's dive right into the syllabus. So important info, this is an online class. If you are watching this lecture in an actual classroom, I think I don't know what's going on. This is an online class. Most of the discussion will be done online on Discord. Um, I put this up here because I prefer students use Discord to contact me versus emailing me. I have a very busy email inbox due to work outside of what I do with RIT, and I tend to check my email accounts periodically throughout the week. And so if you're trying to contact me about something pretty urgent, there's a good chance if it's on email, I might not see it until it's a little bit too late. So Discord's a little bit better. I get notifications. You can message the group. I've set up a IGM451 channel on the Discord for you all to communicate with one another. And also, and if I'm not available there immediately, or if you're not able to find the information that you need from classmates, or the nature of your information of what you're looking to talk about is private, you can either message me directly on there, or if you really have to, you can email me. But just keep in mind again, that'll be sort of up to how available I am that week in terms of how often am I looking at my inbox. Um, Office hours are made by appointment. I've set up this Calendly link where you will be able to go and set up an office hours appointment with me in preset slots. Keep in mind that this will be me calling you or conversating with you in Zoom. I don't physically live in Rochester. I'm actually based in California most of the time. And as I mentioned, I'll be out here in Hong Kong and traveling all over the place for the next few years of my life. And so uh, most of my office hours will have to be done virtually. Um, if you all feel the need for me to have sort of a coordinated office hours, I've done it before where I've streamed on Twitch and people can come in and ask questions with Zoom and all the technologies all at the same time. When I did set that up, nobody used it, so I went back to individual appointments. You can also multi-person appointment me, I guess. Multiple people can sign up for the same slot. So if you're, whatever, want to meet up with multiple people at the same time and talk about whatever, that's also an option. But if this doesn't work for somebody, please message me and we can discuss what might work for you best. With regards to exams, there will be 3 exams throughout the semester, 1 final and 2 midterms. The specifics of those haven't been yet detailed, and so once I figure that out, it will be communicated on Discord initially and made clear to everybody. Um, in my previous classes that I've taught for RIT, exams were provided on my courses. Given this is an online class adaptation of Chris Eggert's previous course. I'm going to sort of figure out what makes the most sense with him, but this is TBD. So we'll kind of get closer to that, and as we do, then I will announce it and make sure that everybody's aware. If you have any conflicts with exams, please let me know as soon as you know, um, and we'll figure something out. Again, this is an online class, and I want to make sure that uh, this sort of fits into people's schedules, but only to the only to a reasonable level. Um, on the same subject, if you're going to be out for GDC or whatever, you're getting married, I don't know. It's your obligations to make sure that your work gets submitted. If there are real conflicts, things you can't get over, just talk to me. Like, I'm going to be very open-minded about this stuff, but you know, given the flexibility of this course being online and available wherever and whenever you want, I expect you to sort of provide similar flexibility and ownership of when things get done once we agree to that. So yeah, let me know if anything comes up. We'll figure it out. So required text, none. There's no required text. The It doesn't mean that you shouldn't read about this stuff that we're learning in class, though. One optional text that's been highly recommended by the prior teachers of this class are Computer Systems: A Programmer's Perspective. The link is here to the Amazon book. Also, this is very optional. I will be mentioning Rust throughout the semester. Uh, this class has been based on largely C and C++ knowledge. Rust is a new kind of emerging systems level programming language that seems particularly promising. And so the book is free. It's just online, and it's just learn how to write some code in Rust, which is pretty cool because a lot of the system stuff that we're talking about you can just download as a crate in Rust parlance, where C or C++ do not provide a packaging repository like if you're familiar with Ruby or Python or JavaScript, right? Many of these modern languages provide ways for you to integrate packages from the rest of the world. C and C++ have not ever really cracked that nut, although we're always talking about how we will one day. Rust has, and also includes things like a build system and some really cool new things, yet at the same time is still a statically typed language, and is a very, very powerful systems development language, although kind of early. So if you're interested in that, and it won't be core to the class, then use get that and check that out. Prerequisite to this class is IGM451, which I taught last semester. In case you were in my class, I'm sorry. That was my first class I ever taught. Hopefully you learned something. But for the most part, if you've taken that class, you'll be good for this one. So a little bit of what we're going to be talking about, and with an asterisk because we'll probably add things that aren't on this list, or maybe not go to all these details. We'll talk about information representation. That is, how do you represent information on a computer system? We'll talk about architecture of systems. We'll talk about what CPUs are made out of. We'll discuss a little bit about assembly language. We'll obviously go into what an optimization on the CPU means. We'll define memory and how to talk about how caching works. We'll even get into some wacky, C and C++ concepts that you may not have heard of. We'll talk about hashing and regular expressions and parsers, which is a fun subject. And we'll definitely get into threading and concurrency slash parallelism of programs, which, by the way, just to kind of plug Rust again, Rust has sort of threading concurrency built in a way that is lauded as being better. So yeah, check that out if that's one of the subjects that you're particularly interested in. Let's go through the syllabus. So, well, I guess we just did, but let's go through the syllabus again. So I'm not the primary author of this course. If you took my 309 class last semester, I am a part-time RIT adjunct professor. My main job, which I'll talk about in a second, is a real job. So I did not rewrite the content of this course. I do review the content pretty at a pretty detailed level. I'm only teaching one class this semester, so that should give me a lot more time to kind of focus. But I did not come up with the original content and material for this class. The goal of this class is to really provide insight into why things work the way they do, in particular in a large scale system, and in particular with real time being kind of at the core of that. We're going to talk about how things fit together and how they sort of layer at these different levels, right? Such as, well, how does the compiler like deal with memory, and how does memory fit together with the CPU, and what's the overall architecture, and what does an operating system do, and why are programming languages designed the way or work the way that they do, right? So the goal is to sort of you give an overall picture. There's a lot of stuff, right? You can't just go into a garage and build a computer with all the pieces from scratch in a very limited amount of time. And I would know this is what I did my master's thesis in. If you're ever interested, I'll be happy to point it out. I think there's a link in here somewhere to a piece of it. But yeah, the goal is to sort of have a more high level perspective on how things go, understand how the underlying system is running your code, because that's how you write good code. Um, so it's a lot, but it's really important, right? We want to know why optimizations work the way they do. You've heard of people, talk about, oh, we had to optimize the performance of the system. Like, what the fuck does that mean? Well, what it means is that they had to do a lot of the stuff that we're going to learn. And then there is a sort of method to the madness, so to speak, in what an optimization is and what's a good idea and what's a bad idea. Um, we talk a little bit about sometimes when we're coding how some code is performant, some code is not, how configuration can affect what you're working on. And that's also going to be something that we discuss and hopefully get a kind of a feel for. Like just in the next week of lectures, we'll be talking about floating point, and how that works. And for game development, understanding the limitations of floating point numbers is actually really critical. And also knowing about alternative approaches to representations of decimal numbers, which do exist. There's not just one way to do things. The real goal here is to sort of see beyond the surface, right, and understand how do we get to what we want? How do we get to a system or a program or a method to do the things that we want to do elegantly, and to hit most importantly, to hit the specifications that we outlined, right? There's a theory, there's like a saying, right? You can build anything. It doesn't mean it's going to work. So you need to understand the limitations, trade-offs of modern computing systems to best suit what you're trying to accomplish in your application, in your company, in your project. This is my first time teaching this course. This slide was here before. Pretty sure Chris taught this class before, but doesn't matter. But this is my first time, so I am adapting the material. Like I said, I'm more of a part-time adjunct. I will be using materials that I got from Professor Eggert, as well as that he based originally on material from Professor Bayless. I will add my own perspective on things, so it's not going to be like a one-to-one. It's going to be like a one to, 0.9 or something. For example, I'll mention Rust, and that's new to this course, but I do think it's critical that it's at least on your radar to know about some of the other things that are going on in the world of systems programming, which, by the way, doesn't change very often. So that's why it's exciting to include something like Rust. Um, and I may make changes to the materials as I see fit throughout the semester. And if you have any feedback, if there's any particular subjects you guys want to sort of dig deeper on, you want to talk about more, you want to explore further, yeah, just let me know. I very much welcome feedback, and will do my best to sort of meet that feedback as is possible. What are my expectations? Well, you probably should know some C++. You probably used C++ before. Maybe you are kind of aware of what's going on with C++ 11. You probably don't know everything about C++ 14 through 20. But yeah, it's always a good thing to kind of brush up on what's going on in the wider world of C++ and whatever. You are probably have used Visual Studio once or twice before, especially if you're in 309. That's kind of an expectation. You know what a debugger is. you may not have used the profiler as much, which we'll talk about later and actually in this lecture. But you know, optionally, if you want, you can attempt or provide code or whatever for this class in either C or Rust. I will put up with it, but you know, that's on you. I think most of the core of the class is in C++. Um, this class is a homework and exam-based class. There's a lot of material to cover. Homeworks will be extensions of what we are doing in class, and they'll be designed to be completed in about a week to 10 days. There'll be 2 exams and a final. And there's no homework from last week or for the coming week. The homeworks will be posted to my courses, and yeah, and also we'll have the assignments due on my courses as well. So, simple rules to this class: watch the lectures, do the homework, and do the exams. That's really it. This class did have a participation trophy when it was being taught as an on campus class, but we don't have that rule. So the participation trophy has been reassigned mostly to the homeworks, I believe, in the syllabus. And there is still 5% of your grade that is sort of, you know, going to be under scrutiny from me of, well, did you try to make at least one office hour? Or did you message me at Sunday night urgently, expecting me to answer immediately and then get angry at me for not answering on a Sunday night? Yeah, don't do that, please. If you want to contact me, do so at a normal time. So yeah, there is still a 5% participation in the class that is mostly just for me to assess whether or not you were trying to participate in a conducive way. In the previous classes I've taught, I didn't have that, which I regret now. So a little bit about me. This is my second semester of teaching for RIT. Cool. I got my BS and Masters in Electrical Computer Engineering from Cornell, although I did start coding really young. Before that, I've been in Silicon Valley trying to build crazy stuff. So let me get some of this stuff out of the way. Here's some stuff that I've built, and here is stuff that I've helped out with. And actually, the bottom left corner, that is an image of Sandbox VR, where I currently stand as the Chief Technical Officer. And so that's what I'm currently working on, which is location-based VR. If you have any questions about that, I'd be happy to answer them. And this is stuff that I'm personally very interested in, machine learning, in particular, deep learning. Yeah, that's about it. Excited to be teaching this class. This is stuff that I'm actually personally very passionate about. I love system stuff. Like I mentioned, I did my master's thesis in it, which I'll probably talk about sporadically throughout the course. And it's also, to me, some of the more interesting subjects in particular that are very challenging. Like you do have to kind of come up with really unique ideas to overcome performance limitations or memory limitations when you're building aggressive or challenging applications. So let's get into it. So what is a computer? Most modern systems, and I say most because not all computers are von Neumann in architecture, but most of them, in fact, like any computer that you've used, most likely is a von Neumann computer. You've got a central processing unit, which is interacting with a memory unit, and you're able to interact with that through an input device, and it's somehow outputting its data as an output device. If any one of these components is missing, then it's not really a computer, right? You can sort of argue what an input device is then. Is it a keyboard, or is it something else? Or what an output device is. It doesn't necessarily have to be a display. It could also be something. But in a sense, if you think about it almost like an organism, right? You have a thing that takes in some kind of input and produces some kind of output. Otherwise, if it doesn't produce an output that you can't observe that the internal system is actually doing anything, so it's not a computer. And if it doesn't take an input, then, well, it doesn't know when to start or when to turn off. And so, again, it can't be a computer. To kind of dig into some of these like subcomponents, right? The control unit tells the arithmetic unit and the logic unit what to do, and the memory basically drives the whole thing because you have to have places to put your data to load them from, and also to tell you what to do next, given insufficient information from the environment by way of the input device. So, yeah, a lot in this very simple little diagram is captured, but it's actually, this is a full computer. Um, Going into a little bit of a more detailed look, and you can see it's not as simple as just that, right? Generally speaking, in a computer, you've got a processor, and the processor is composed of what's called an ALU, or arithmetic logic unit, that's powered by general registers. These are just sort of local memory next to the ALU. You've got an instruction decoder, which is connected to the control unit, which then feeds instructions from the memory, which is usually provided by some kind of bus. And you've got this thing called the DMA controller, which is the direct memory uh, access controller, and the clock, which drives the whole thing. If you start, and now you're starting to get into computer architecture. If you're interested in computer architecture, this book by Hennessy and what's his name is really good. And also, if you're really interested in this stuff and how to build this from scratch, there's a terrific Coursera class that's free called NAND to Tetris, which will let you go from designing a NAND gate, which a NAND gate is a logic gate that is at the core of most circuits, like digital circuits, and going from NAND all the way up to writing some Tetris that runs on a computer that you've designed and built. But yeah, this is already starting to get pretty detailed, but it gets even further detailed, right? Like, for example, you can have multi-core architectures of a CPU with multi CPUs on it, and with what's called the cache sort of hierarchy, right, where you've got caches at incremental tiers of where at each tier you've got a higher I/O latency of that, and so on. Um, and then finally, you can start to see all the more complicated systems and peripherals. Like in this case, you've got a quad core that's connected to, um, the SATA controllers, which is what you connect to your hard drive to, and your networking, and you can sort of see how systems, the computing system, is a lot more complicated than just that little block that we kind of drew out, and it can go to sort of infinite complexity if you want. But we're not going to go that far, right? That's computer architecture stuff. If you're interested in it, go check that out. But what is important is to really understand sort of the architectural impact of the computer, um, and how it works. We don't need to know all these different pieces, right? Like, we don't need to know the specifics of the USB protocol, right? If that's something that you're interested in, you can go and learn more about that, right? We don't need to necessarily know exactly how the NAND flash works and how the controller connects to our CPU. We just have to assume that all these pieces sort of connect to each other, sort of like that. That's sort of the level that we're going to be operating at. So, um, we need to, you know also, uh, the architectures get really complicated, um, but we don't necessarily need to operate at the machine level either. So we're talking about the CPU and how it interacts, and we're talking about the ALU. And again, that's a subject of like a computer architecture course. But what does the CPU actually operate on? Well, you can imagine that it's not operating on, if you're familiar with C++, it's not operating on, for in I equals 0. It doesn't know what that means. Like a machine is just a bunch of transistors. It doesn't know just read and understand just like you and I do. Um, what CPUs usually operate at is what's called machine code. Machine code is the actual binary. It's literally just a huge number, right? A 32-bit or a 64-bit number that somehow encodes everything the CPU needs to know to do a particular instruction. Um, this 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 machine code number, just a number, needs to include everything from the type of operation, right, to the operands of that operation or targeted registers or whatever else the CPU needs to know to kind of change its state to enact that next step. Um, Before modern computing, this was actually accomplished by punch cards, right? So it's just literally you had a punch card, you'd pop into it that number was just an encoding of a number, and then you would create these stacks of these punch cards that were manually fed into a computer, and the computer would then be able to detect the value based on the punch cards because there were holes in them, and then it would update an internal state and rinse and repeat, and that's how you wrote a program. Shortly after that, we started to see onboard memory. So you had a memory chip, but it was sort of random access memory. So when you turn off the computer, it obliterated. And so you had to manually flip switches and enter your program operation by operation, just like a punch card, except you didn't have to have punch cards at least. You just sort of had to save them. And then you can run the program and you can kind of see the state of the computer based on like blinking lights on the front of the computer. The MSI was one of the first sort of consumer computers that you were able to buy and do this at home. You know, it only cost a few $1,000s back in like before the 80s. So yeah, so instead of like being at that level, we kind of want to abstract it. You're already familiar with C and C++, and we can write this code. So, wouldn't it be nice to be higher up than a bunch of numbers? So if, without knowing the specific implementation of the CPU, we want to be working at this level of like add, subtract, save, delete, right? And then we don't have to know what the CPU is doing underneath. We can just sort of tell it, hey CPU, add 5 and 7, or hey CPU, load register 2 and then add 20 to it and then save it in the register 5, right? Whatever, like a bunch of stuff like that. That's where we want to be at. We're not quite at C++ where we're creating classes and casting them into other classes, but we're already doing much better than having to memorize all the operations and the machine code that we need to get the CPU to do what we want it to do. So how do we abstract this? How do we turn machine code into assembly, as we would call it? So if you remember those verbs from before, like add, assembly sort of turns that into add register 1 and 255. And this line, this is assembled by an assembler, or it could be a human being just copying it from one place to another, and that's assembled into something like 0401FF in hexadecimal. What we generally have here is we have what we call a opcode, and the opcode here is 4. 4 represents an add, and then the next, the next 8 bits are going to say 1, and that's referring to register 1. And then the next 8 bits is going to be the value of 0xFF, which is 256 in decimal. And so the combination of this taken by the CPU, there's a component of the CPU called the instruction decode, right? It takes that instruction, right, and parses it out into the opcode, the register, and the decimal or the operands, and then the CPU as a machine knows how to do this. And so already we are in assembly language, and the assembly language is able to sort of say, do this thing with these things. I actually did a big portion of my master's thesis on this subject. One product of that was this thing called the System on Chip Toolkit, and I included a link down and below, which, if you're interested, I still think has good documentation on what a sort of minimal set, what's called instruction set, or ISR, instruction set architecture, ISA. So if you want to take a look at that, it kind of talks pretty well about what some of these opcodes look like. And if you want to kind of explore that more generally, I recommend taking a look at MIPS, which is what's called a RISC architecture, which means that every single instruction takes the same amount of time on a CPU, which is important for what has led to ARM and real-time kind of processors. So from the assembly, we can now move up into slightly higher level programming languages like C and C++. Now, this helps us kind of focus more on the programming side, but we can't quite ignore the underlying architecture, right? As you know, right, even though we write code in C and C++, the way that the computer sees it, the CPU still sees this kind of stuff. It still sees 0x0401 FF, right? As much as we'd like to believe that we're in this abstract, beautiful programming language land, there are things that we can do that will pop that bubble, even though we're writing in languages like C and C++. So, for example, right, if I'm writing certain code, it may be non-performant. So, say my CPU does not have a floating point unit, which means that my compiler, when I write my code, will have to replace any floating point operation with a lot of code, right? There are algorithms that let me add and subtract floating point numbers, but by comparison to an integer or what's called a fixed point number, they're extremely slow. Um, so if I don't have a floating point unit and I don't know that, and I write a program that's trying to render 3D stuff with floating points, and then I hit run and I get like one frame every 5 minutes, I shouldn't be surprised, right? So you do need to kind of know what's going on underneath your code, so that you can write the right code for the right job. We can't quite get away from those ambiguities, and also the conventions that we agree upon in code. The CPU is not always a given. So here's a really simple and silly example, and I think this is in my courses, and if it's not, please let me know. But this is the entire example. You can see a simple function, which is just printing some parameters out, and then returning the sum of them. And this line of code, which is calling that function with the val 10, but you're using the increment, uh, the actually the post increment operator with it, and then below a slightly different approach where we're doing the pre-increment, and we're evaluating it that way. And so when we call this, right, we'll see that there are it's sort of not not exactly predictable necessarily, especially if we're in debug versus release mode. And the reason is that there's no strict convention in what order do these operators get acted upon on the value. So in the top one, we're going to get the same result because the post operator is going to add one to val 3 times, but only after we call the function. So it's going to return, 30, and then val is going to be equal to 11, 12, 13, right? But below, um, we're going to have it return the same. The return value is going to be predictable because it has to be, but A, B, and C may receive different, may get their values in a different ordering each time that we run this. So the language itself just doesn't provide a definition, right? We in C++, the order in which the kind of pre-increment operator is applied is not always the same. The post one, it's also not always the same, but it has no real meaning, right? Because the values received by the function will be the same, and ultimately we're guaranteed that all three operations will take place. But in the second one, while we're guaranteed that all three operations will take place, we're not entirely sure in what order, and so the value and the return value may be well, it's not never going to be different because the values are going to be guaranteed to be sort of the same number of operations, but A, B, and C when printed, we'll see sort of different things. It's not really um, a good idea to write code like this. Obviously, you can avoid this. This is sort of like, you know, pretty clear. that this code is sort of, why would you do that? But at the same time, it compiles, it runs, it's possible to do, and languages have a lot of stuff like this. Like if anybody has written code in JavaScript, for example, you know that in certain cases, the conversion of variables from one to the other makes zero sense, where when you add an array to a string, you get not a number or something. It makes no sense. So this happens pretty often, actually, in programming languages, and it's just up to us to make sure that we write code that is sane, and also works off of the underlying the assumptions of the underlying system. So another thing about this, right? What happens if we compile the code with different build targets, right? So in debug mode, a lot of the funky stuff that we talked about happens, but in release mode, something else will happen. And I recommend this as just an exercise for you. Like I mentioned, I'm on the wrong computer to demonstrate this code right now. But what will happen in release mode, the reason release mode will change the output of your program is because it enables the optimizer. And the optimizer will take a look at both the code itself, meaning the C and C++ code, and say, okay, there's stuff going on here that shouldn't be happening, and we can circumvent this and we can avoid that. But sometimes the optimizer will actually look at the assembly code itself and notice that certain code paths are not doing anything, and sort of look for certain patterns that then circumvent code paths to speed things up. And when that happens, you'll notice that in release mode, you will get a different output than in debug mode because it circumvents a lot of that in between code the debug code will produce, which results in that sort of confusion and what will ultimately happen. And release mode often is much more robust and reliable, meaning when you run the program multiple times, you'll get the exact same thing each time. You'll have less, it's called race dependencies. But it's not always predictable by comparison. From debug to release, a lot of times you'll notice that it's not everything is predictable, given that the optimizer will go and clobber certain code paths. So if you've written real-time C++ with Visual Studio for 309, you're probably very aware of the unpredictability that is presented by the optimizer. But it's not unpredictability, it's just the optimizer will get rid of code that's not doing anything. So I'll mess around with this a little bit and see for yourself. So why? Well, like I mentioned before, right, the C++ does not really prescribe a execution order for the parameters. It kind of comes in whatever order it sort of ultimately decides. Uh, but the optimizer, when in release, will enforce certain things, and so again, uh, this this is kind of a stickler point to make for now 5 minutes, but it's actually very important in its principle, right? The optimizer, especially when you're like writing code and you're trying to test it and you don't see anything change, and then you just realize that the optimizer is just cutting out your code path and it's actually not doing anything. This is something to really pay attention to. So if you want to see this again, we're going to talk a little bit about another example, which I'm again not going to give you a demo of in the debugger, but I do encourage you to do this. So to turn off in release mode the optimization, you go into your project settings in Visual Studio, and under the C and C++ tab, you can turn off optimization, as you can see. And so now if we take a look at these two functions, which are pretty much the same code, except on the left, we're indexing this, two-dimensional array with I and j, and on the right, we're indexing into this array j and I. A very, very slight difference, but keep in mind that the nesting of the two loops is exactly the same in both cases. So logically, this is doing the same stuff, right? It's going through all of the values of this 2D array, and then setting it to 5. So you'd think that it should work the same. But it actually does not, especially for large numbers of this. In if this array is a very large size, right? This one of these functions is actually significantly slower. So I'll let you for a minute think about which one it is, but the answer shouldn't surprise you. The second one on the right is significantly slower, and that's because of the way that memory is structured, right? If you think about a 2D array as, you know, kind of like an array of arrays, right? So you've got, if it's integers, say it's a 10 by 10 array. So you have 10 integers and then 10 integer arrays, right? So the way that, for me to go from one value to the next value is going to be sort of plus 1. Whereas when I want to go from one array to the next array, it's going to be plus size or plus 10, right? So you can see on the left here, what we're doing is we're kind of largely staying on the same line for each value. So we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. And on the right, we're sort of going line by line instead. We're going, you know, 0, 5. I'm assuming 5 by 5 instead of 10, so I don't have to count so much. But 0, 5, 10, and so on. Now, as that number gets bigger, right, you may think, well, what's the big deal? Like, I can count to 5. Computer can do that too. But when the computer gets bigger and bigger and bigger, we're talking about bigger and bigger jumps between the data. And now you start to get into caching the data, making sure that data is local to your memory, and things like that, and the optimizations that you can get out of compilation uh, when data is next to one another, and the kind of tricks that the optimizer takes can do. And so as a result of that, all of these little things that the compiler can do and the architecture of the computer underneath you, you'll find that array1, this function, array1 on the left, is significantly faster, significantly, which is surprising if you're not aware that the CPU may handle the two things very differently. And we're talking about a very minor change in code. So again, this kind of comes down to how does the language store this 2D array, and also how are the memory, the cache, and the CPU connected to one another, and how do they get impacted when they go through something like a large memory chunk that is potentially large. Like, also, at what point does it start to slow down, right? At one point, if it's a 5 by 5 array, I guarantee the amount of time is going to be the same, right? Or imperceivably similar. So like, at what point do we start to have what's called cache misses as a result of this? What is a cache miss? And then we'll be talking about that in this class as well. And so another thing to kind of keep in mind, that sometimes it's the opposite, right? So in C and C++ and in DirectX, the left will be faster, but in OpenGL, OpenGL and in Fortran, the right will be faster. So it also comes down to sometimes the way that the language handles this stuff for you. So you may write some code, but the underlying language will actually be doing something else. So you do need to be aware of what your languages are doing, which is why programming language design is such a hot topic when you're talking about systems, because the way your language works is largely the way that your system works, which is really important. For example, like with Java, Java doesn't have native array, like 2D arrays. It just sort of supports jagged arrays. Now you can do 2D arrays, but that's just more of a design. It's not actually implemented by the underlying language. And so, again, like I said, the language largely dictates the design of the system, even more so sometimes than the CPU architecture. In fact, most of modern CPU architecture has been trying more and more and more to make the underlying CPU less less of a factor in software design. And this is kind of interesting because CPUs, especially modern CPUs, and we won't talk about CPU architecture too much, but modern CPUs do things like branch prediction, and they do what's called like they're super scalar, meaning they do multiple things simultaneously, and they have to sort of figure out code dependencies, because if they're running multiple instructions at the same time, if there's any kind of relationship between those instructions, they do have to take those into consideration. So modern CPUs are really complicated, and yet at the same time, the underlying both compilers and systems are designed such that a piece of software can run in a way without having to worry about all of that unpredictability that is actually happening under the covers, just so that the CPU can squeak out a few percentage points of speed up. So does it matter, right? Like, so does it matter that Array 2 is slower or faster? Well, yeah, it does. I think, especially if you're dealing with large pieces of data like images, and if you're making a video game, which is, I'm assuming, why you're taking this class, well, it's important, right? Just like imagine a 4K image, right, is a huge amount of data. So you will run into these things. You will run into problems where all of your data will not fit into memory. You do need to start to think about how your system is optimized to best suit the performance or the intended goal of your performance, like what's the performance goal of your application. So um, right. Doesn't I'm not really sure what this slide is for. Anyways, will your compiler fix it for you? Yes, most of the time. Compiler optimization is pretty good. Most of the mistakes that you'll ever make, somebody else made before, and they probably made them enough times that it got into an optimizer somewhere. Optimizers will do even more than just fix issues or catch problems. They will also unroll loops, for example. So if you have a loop that's doing the same thing, it'll take that loop and basically duplicate it. So it's um, happening in parallel, or it'll, instead of having the loop to save on the branch, it will unroll the loop so that it will do it, instead of a loop, it'll just do it, sequentially. So for example, if you have a four, like say a 2D array with 100 items, and you're just going through and setting the value to 1, right? The compiler may remove that code and instead replace it with more performant code, right? Like a memset, or just a linear sequence of assembly level sets or something like that. So the optimizer is pretty powerful, but keep in mind it will also cut out code that you don't use. So say your code doesn't do anything, it doesn't output anything, it'll just delete all that code, and so it'll never actually happen. This can have some pretty adverse effects when you're trying to do things that do have impacts, but it's not obvious to the optimizer. So you can see this when you're debugging release code. Often the debugger, your breakpoints won't hit, and you're like, what the hell's going on? It's because the code doesn't actually run. So keep that in mind with the optimizer. Sometimes the optimizer is not your friend. Yeah, so the compiler can't really guess your intent, but it will inline. Like, so for example, a compiler will take the array1 function and it will inline it. And what does inline mean? It basically removes the function header. So when a CPU loads a function, when a modern compiler basically sets up a new function that then the CPU is processing, it has to do what's called a switch, right? It has to set up a new stack with all the variables and set the registers for that function and so on. It's actually a non-insignificant amount of processing that happens when you switch from one function to another function. It's not quite a context switch, as is done with like a changing threads and so on, but at the same time, it's actually pretty similar, right? You're going from one function to a different function with a different stack, with a different sort of, not quite memory space, but almost like a local memory space, as we'll talk about stacks in the rest of this class. that can be pretty expensive, especially if this is a function that you're calling many, many times, right? So often an optimizer will look at your code and say, oh, hey, this seems like a pretty lightweight function. It doesn't really do much. It just takes a bunch of parameters and doesn't create anything internally. And so it'll inline it, which means it's almost like it cuts and pastes the code into where you call it. So it no longer calls the function, and it's way lower overhead. Um, and so, we may want to do the same thing for array, the array2 function. Um, but if this fixed it for us, for example, we could not program an OpenGL, which is column major, right? So we might be doing something purposefully. Uh, in the case of array2, this would mean that if the optimizer fixed this for us, we may get the kind of opposite intent. So it's the compiler can't read your mind, in other words, and sometimes it'll see, oh hey, this is clearly something I can do. I can inline this function, but it's not going to go and say, oh, this guy clearly flipped I and J. I should flip it back, because if it does that, it's a functionally different program. So the optimizer will not change your function, the functional aspect of your code, but it may reduce the size, so it's faster. It may increase the size to make it faster, right? Like I said, it may unroll your loop and things like that. Um, but yeah, so keep in mind the compiler just can't guess, and so you do need to sort of know what your program is trying to do, and if it's not doing that, then figure out why. Usually it's not the optimizer, but sometimes the optimizer will get in the way or skip a step, which is not actually being used. Um, so how do you measure performance? We're going to talk a little bit about this today, uh, given that you may not have used the profiler before. Now, Visual Studio has a terrific profiler. You can actually see how long a program, goes into a particular function and what's going on in that function, and when it calls other functions and how much time. There are different ways that you can use this profiler that Visual Studio provides you, which has an overhead. This is an application, right? This is code that's running inside of your code in a way like the debugger, and so it is not for free. But there are other ways, right? We can also measure uh, time, how long a particular function took to run. We can do this by capturing the time before we call the function, then capturing the time after, and then subtracting them, and then measuring how long that takes. And this is good because then we can sort of profile that particular function. While we may not do this in production code, this is a good way to debug it and to understand how we can speed it up or slow it down if we need to slow it down. So let's talk a little bit about how we would create a application that we can then profile. So the way you would do it, you would create a new console project in Visual Studio 2017 or 19. It's largely the same. And then in the debug tab, you'd go down and you turn on the performance profiler. You should do this before you run the application. You can use the wizard, just set up the performance wizard, the wizard. It's very easy. And you can kind of choose. Uh, Instrumentation is kind of the best one. You can also use CPU sampling that is at the CPU level, and it has pretty low overhead, but it's up to you. All these work. And there are other options as well. For example, you can choose what to profile, whether it be, EXE, a DLL. You can choose which project to profile, and then can finish. And so, yeah, the results are pretty cool. You can see your CPU utilization, you can see the memory utilization, you can see it over time. This is actually, the time bit's actually really useful. For example, if you're making an application that's loading a bunch of stuff from disk and you want to see how fast it's doing it and what it's doing in the background. And then you can also see timing. You can see the percentage that your application is spending in a particular function. You can see how much time is being spent in that function. Um, and you can also sort of debug through it and see which functions it's constituted of, although that's not shown here. So yeah, how does it work? Like I said, code gets added. It's not free. It's low overhead, but it is not free. This does affect your timing. So if you're doing something like real time, so you're doing like an embedded interface or something, or you're doing a lot of threads, this can muck with your timing. So just keep that in mind. Um, the diagnostics window can provide with a lot of us with a lot of really good information, like memory allocation, um, and you know, this you can do this in release, but um, when the program goes away, then so does this window. So you can do a snapshot, by the way. You can't save it if you want, um, but that's actually pretty useless in my experience. But there are ways to sort of save the snapshots post, and then you can review that after you've run your application. So that's not entirely true. You can save this after it goes away. Um, you can also do your own timing, like we mentioned before. All we have to do is measure the time that it takes for a particular function to run. To do that, you measure the time before, the time after, and then you subtract them, and that will give you the time elapsed. So pretty straightforward, right? Chrono is the standard library for C++ that lets you access the high resolution clock. Um, if you're not already familiar with the auto keyword, it can be very useful when dealing with chrono because the types, as you can see below, are really long. Like SED chrono duration double. It's like, okay, auto start, auto finish. You just take the now, right? And now we have the elapsed. We subtract finish from start. Now, the piece that's missing in this code is you would run your function between start and finish. Because right now, it's just measuring how much time it takes to start and finish, which will hopefully be close to zero, but not quite. So just keep that in mind. These functions do take their own time, but given that we're using this generally to profile, that's going to be discounted. In other words, we're going to be looking for change versus absolute values. Now, if you want to get absolute values, like how long something takes, you're just going to have to live with this overhead that this or any profiler is going to take. You just have to assume that your underlying code, when you take away profiling, when you take away, when you build it in a release, when you turn on the optimizer and all that stuff, it's going to be faster. So there's no real way to completely predict what code's going to do in production, right? The key is to build a system and a robust system that is able to deal with fluctuation um, in performance. So, just because something you're not going to be able to ever measure it exactly to the tick doesn't mean these things are not valuable. But it does take a little bit of getting used to. Your code may run on somebody's mobile phone. It might run on somebody's desktop with, two GPUs. It may run on somebody's 32-bit ARM processor at 80 megahertz. You don't know. And so to build a good system, you kind of have to build a system that is robust for those different sort of scenarios, or define the specification very, very clearly so that okay, this code only runs on this particular set of expectations. So let's talk a little bit about languages. C, C++. This is one of the better. These are one of the better languages for the portability. Um, but it's not perfect, right? Data types are not all the same size in C and C++. A particular computer may define an int to be 32-bit, and another one may be 16-bit. There's a lot of non-standard libraries that are built for C and C++. You may have written your own, for example. Hardware may be big or little endian, and the language doesn't generalize that. Um, the operating system calls may be different as well, depending on which operating system you're on, and things may have different name conventions. And sometimes, and actually very often in C, you'll have very specific architecture code, meaning the code does something that's specific to a particular CPU that it expects. This is particularly common in like older video games that were running on x86 and were able to sort of take advantage of extensions when they're available and not. And in fact, it's still pretty common in that a lot of you know um, video games are using specific extensions in GPU hardware. Now, a good system turns that on and turns that off when it's not available, right? But as applications can be quite complicated and large, and when you don't handle that explicitly, or if you forget to, or something changes, then boom, code doesn't work anymore. So as much as we're going to start to try to say, oh, this is the way and this is the standard, unfortunately, reality, in theory, everything should work, but in practice, it doesn't. I want to talk about a little about Rust. The nice thing about Rust is that it solves a lot of the problems that C and C++ have. For example, has packaging, a package system. So to the point of having non-standard libraries in C and C++, Rust does have a sort of centralized package repository, much like npm for Node.js, or gems for Ruby, or pip for Python. What the package system does in the form of crates is it tries to generalize the way that libraries are built. So even though there may be non-standard libraries, the way libraries work is standard for the most part. If you have the right dependencies, things should work. It's not always perfect, but at least Rust is trying to build that for C and C++ type languages, for system design languages. Um, Rust also has a built-in build system. So, as you know, C and C++ have compilers and linkers and assemblers and you name it, but they don't have a standard way of using those things. Visual Studio is an IDE, so it integrates all of those different components for you for C and C++. But Rust has a system called Cargo, where you literally go cargo build and it builds you your code and it does it automatically. So it's actually quite convenient, and it's a pretty common feature in a lot of modern languages. But C and C++, nobody's quite agreed. This is more historical, I think, than any other reason. This is my opinion. Is that there were, when C and C++ were developing, there were so many competing companies trying to build compilers and assemblers for C and C++, that there was no consensus on what a build system and a package management system looks like. But now in sort of modern programming, where people realize the value of the compiler is not, nobody's selling a compiler. Well, maybe a few people are, but it's not common. And also Rust presents common consistent types, just by virtue of having the type systems that we are now know to work in C and C++. Rust just has that built in, whereas C and C++, these are provided by external, standard, but external libraries. Um, Speaking of data types, you can kind of see we've got different sort of combinations, right? Short on most systems, except for one by way of this diagram, is 16 bits, and int is usually 32, but sometimes 16, sometimes 64. A long is usually 64, but sometimes 32. A pointer usually is the size of the native size of the architecture. So if you're on a 64-bit architecture, the pointer is 64 bits. If it's 32-bit, then you're 32, and so on. And a long is just the maximum on all systems. And you can kind of see how this is different for different computers, which is problematic, right? Because if we want to write software, we kind of want to know that it works everywhere. When types are the wrong size, generally speaking, things just fail. That's because you're not going to check the size of your type every single time you use a variable. Your application would just bloat to being way too big. So what's kind of happened in C++ land is, there's a standard definition for types by way of standard int. Um, for certain things like size t and pointer diff t, these are types that are designed or designated for a particular thing. So size t is like an index, or the pointer diff t is like a pointer. And this is also, by the way, why a lot of APIs and frameworks will define their types with a type def to ensure compliance. So, for example, OpenGL will define GL float. GL float may be different sizing on different platforms, but then the underlying system of OpenGL will know. Well, I'm sorry, a float may be different site types on different platforms, but the GL float will always be the same type. And OpenGL as a framework can write code to detect when which type to use, or write custom code for certain things. So this is actually a thing that Microsoft handles too, right? If you've seen DWord and Word and all the weird Microsoft types. That's why they do that, is so that they can ensure that their code remains compliant on whatever CPU architecture they need to support. And Windows historically has been the best at, dealing with, you know, every hardware configuration under the sun. That's one thing that they've actually done really well. Microsoft gets a lot of negative press for Windows not working here and there, but they have a very, very hard problem they have to solve, which is their software has to basically support, you know, every motherboard and every GPU and every CPU and everything that anybody makes anywhere at any time. And so, what they give up in reliability, like with Mac, where Mac only has to run on a very limited set of hardware, right? Windows is just massively more flexible than Mac has to be, right? But it's not perfect. Whereas Mac, it can be a lot more perfect because it can predict, like the engineers can predict and test all of the different hardware configurations that code has to run on. There's a nice little link here that talks about size T and pointer diff T. It's basically, like I said, these types have very specific use cases. So size T is usually used for indexing and for counters and for things where just a size. So like what size is an array? It's usually the unsigned max int type on a particular system, and same thing with the pointer diff, which is the sign max int type obtained by size of. So it's very similar types, and so yeah. Cool. So one thing we should talk about is the difference between 32-bit and 64-bit. So here, if you run this on a 32-bit project, the value you get back will be 3. And the reason is pointer equals pointer plus a plus b is simply going to move the pointer location to the left by 1. So it's pointing at 4, and then you're pointing at 3 because you're subtracting 1, because a plus a, which is -2 plus 1, is -1, right? So then you see a 3. But if you change it to 64-bit, what will happen? So feel free to pause and try this for yourself. But the reason it doesn't work is because on a 64-bit system, the extension of the int to be a 64-bit value, I'm sorry, the int will still be a 32-bit value, but the pointer will be a 64-bit value. The compiler might resolve it for you correctly, but for the most part, the auto conversion to unsigned will just give you this garbage number, and it'll blow up. Your system will just blow up because it's going to be -1. It's going to be all F's, and then bleh. It's just not going to be good. So to correct that issue, you want to use size T or pointer diff T for the math. Instead of using int and unsigned int, you would use size T, and that would solve your problem. Yeah, so that's it for lecture 1, or week 1, really, of lectures. Hope you enjoyed it. Whoa. Um, and yeah, this semester we'll talk a lot about systems and architecture and how to build good code and why the code we write works the way that it does. So with that said, looking forward to a great semester with you all, and hopefully next time I won't be in a hotel room. All right. Thank you all. And if you have any questions, please hit me up on Discord. Email me if you have to. And also, lectures should be up at the same time that this lecture slides should be up at the same time that this lecture is posted. Cool. See you all soon. Bye-bye.